This is Lecture 6, Chapter 3, Section 3.2. In this lecture, we're going to talk about moment of force about an axis. So you may recall that in the previous lecture, we talked about the moment of force about a point. So in this case about an axis, we're just going to add one extra step, but otherwise the calculation is fairly straightforward. So before we jump into that, we want to recall the idea of a scalar product. So you may remember from your math class that when you dot product two vectors, you end up with a scalar value. And so this first equation I have listed here, P dot Q, then we know that in order to get that value, we just simply take the X components, multiply them, add them to the Y components multiplied, and add them to the Z components multiplied. Now we know this because if you I dot I or J dot J or K dot K, it's equal to 1. This second equation is how we can relate the angle between the two vectors. So we know that if we dot product the two vectors, it's the magnitude of that is going to be equal to the two magnitudes of the respective vectors multiplied by the cosine theta, where theta is the angle in between. Okay, so one of the things that this chapter does is it jumps right into moments about lines and talks about the idea of projection. So before we do moments about lines, though, I want to present the idea of a of a force projected onto a line. So for example, here we have force P, and if we want to know how much of that force P is projected onto the line OL, then that can be calculated simply by taking the dot product of the vector P dot product against the unit vector of the line OL. And so that subsequently gives us the magnitude of how much force P is actually on the line OL. Now we could take that one step further, is once we knew that magnitude POL, we could multiply that by the unit vector OL and actually get the actual directional vector. So I know that's a little bit to absorb in all at once. So let's look at a quick example and show you the math involved. Now in this example, we have a force given -6, 9, 3 components and units of kilonewtons. And we have this force going off to the right here as it's shown. And we want to know how much of that force is projected onto this line AO. So here we have AO. We have clearly delineated points of where it's located in space. So we're going to find out what is the magnitude of force on AO, and then what are the components of that said force. And then finally, we're going to find what is the angle. So here's our problem. And if you need to, you can rewind and look at the picture again. But so I've sketched out the schematic of it. And so you can see here is the force 6, 9, 3. That's in kilonewtons. And then we're trying to find the force AO, scalar, the vector AO, and that angle theta. So we'll kind of cut this off so we can move along. Let's put that up there a little bit. Actually, so we know that our governing equation is FAO equals the vector F dot product with lambda AO. All right, just like before. So we want to know what lambda AO is. Now, you know this from the first chapter. To get AO, it's just simply the location. And so we know that in order to go from from A to O, because it's AO, we go -1 in the I, +2 in the J, -2 in the K. So if we take the magnitude, that's 2 squared plus 2 squared plus 1 is 9, root is 3, so divide that by 3. So we basically have 1/3, 2/3, 2/3 is our lambda AO. So we go ahead and dot product, we know we have FAO equals, and we'll go ahead and write negative 6i plus 9j plus 3k dot product with negative 1/3 I plus 2/3 j minus 2/3 k. Okay, so there we have that. And a little closer. So there's that. So if I go ahead and I multiply that through, multiplying this, the i's, j's, and the k's, I end up with 6. Okay, so 6 kilonewtons. That's my magnitude. You can check that. So we know now that our FAO is equal to 6.00 kilonewtons. So that's that answer. So that's the first part. So then we want to know what is the vector AO. So that's easy enough. If to get that, we just say we know that FAO just equals the scalar AO times lambda AO, right? And so that's going to be equal to 6.00 and then times minus 1/3 I plus 2/3 j minus 2/3 k. And I guess I should say I hat, j hat, k hat. Sometimes I don't do that, but I guess, yes, technically it's a unit vector, so it should have that. So if we go ahead and multiply through, what do we get? We get negative 2i plus 4j minus 4k. Or our final FAO equals negative 2.00i plus 4.00j minus 4.00k, all in kilonewtons. And there's our answer. So again, we started off finding the scalar just by doing this dot product. Negative 6 times negative 1/3 gave us a positive 2. This gave us 6. This gave us negative 2. And so the net was 6. So that's our magnitude. Then when we wanted to find that as a vector, we just took its magnitude times its unit vector, which was this. Get that? And that's our final answer. All right. So the last thing we want to find on this problem is what is theta. So that's the angle in between. And so in that case, we know that cosine theta equals the dot product of each vector divided by the magnitude of each vector multiplied together. Okay, and that's just that equation I showed you on the slide. So if I find the magnitude of f, turns out that the magnitude of f, remember the original vector of 693, so f equals negative 6 squared plus 9 squared plus 3 squared square root, and that gave me something like 11.23. So I know now that if I multiply this, I end up with negative 6 times negative 2. And this is, again, I'm taking the I component of F and the I component of AO. So, and then I'm adding that to the j component of f times the j component of FO. So plus 9 times 4, and then plus 3 times negative 4. And then divide that by 11.23 times 6. Okay, so I end up with inverse cosine minus 1 of 36 over about 67.34, giving me a theta of about 57.7 degrees. So hopefully that's pretty straightforward. Again, the dot product, whenever you see this, you know it's just the I components multiplied and the j components and the k components and then respectively added. So if you practice this, you should have no problem with that. All right. Okay, so this is another example. And in this example, it's identical to what we've done. And so you could go ahead, I would say, is take the time to practice it and go ahead and do the problem, because it'll help you. If you can walk yourself through this whole problem without having to look at the solution, then you should be in a good position. So go ahead and do that, and once you've worked it through, come back and you can check the solution. Okay, so you're back. All right, so there's what the problem looks like. That's what we had. So we know that we had the 56 newtons going from A to D. We had a line going from A down to O. And so we were given that 56 newtons is the magnitude of this force AD. Make that a little more sharply. Now it's even more like an O. Maybe that's better. And so we're going to do the same thing. We're going to find what is the projected amount of this 56 newtons onto this line AO. What is that subsequent vector in IJK components? And what is that angle theta? Now, you already have done the problem, hopefully, so you know exactly what I'm going to do. But let's walk through it anyway. Now, in this problem, we have, again, our governing equation. That's the first thing we're going to do. And so, but let's find, we're going to need both the unit vector for AO and for AD. So let's find that first. So we know that lambda AD is going to equal 1.5I minus 3J plus 1K. And if we divide that by its magnitude, that's going to be 3.5. We're also going to need lambda AO. And so that's going to look similar. It's going to be 1.5I minus 3J and minus K. And that's all going to be over the same 3.5. So we have those equations. We're going to come back to them. So the first thing we want to do is figure out what is F. So the force F as a vector is just going to be 56 times this unit vector AD. So times lambda AD. So let me write, so lambda AD. So F equals 56 and then times 1.5 over 3.5 I minus 3 over 3.5 J plus 1 over 3.5 K. And so with that, we should get 24I minus 48J plus 16K. All right, so that's just our force. All right, now we have it as a vector. So now what we're going to try to do is we want to go ahead and figure out what the projection is on AO. So we have F, we needed that because recall in the last problem we were given that. So first we had to find F in order to do the dot product of it. So now we know that FAO is going to equal then the 24, negative 48, 16 dot product against the 1.5 over 3.5, negative 3 over 3.5, and negative 1 over 3.5. Okay, so there's AO up there. There it is down here. So we'll just dot product that together. So if we do that, we end up with 10.29 plus 41.1 minus 4.57 yields 46.8. And so we have 46.8 newtons. That is our projected FAO. Okay. Now, if we want to figure out what that is as a vector, then we know that if we want FAO, that just equals FAO times lambda AO. And so if we get 46.8 newtons, and then we know lambda AO, 1.5 over 3.5 minus 3 over 3.5 minus 1 over 3.5. Then we end up with FAO equals 20.0 I minus 40.0 J minus 13.40 K. And that's in newtons. So the last part is just, again, the angle. Same idea. Theta equals inverse cosine minus 1 of F dotted with FAO all over the scalar F times FAO. And so in order to get that, we end up with theta equals inverse cosine minus 1. I'm sorry, inverse cosine of 24 times 20. That's my I component, plus 48 times 20 J component minus 16 times 13.4. And then all divided by 56 times 46.8. So we end up with theta equal 33.5 degrees. Okay, and there you have it. So went through a little quick, a couple practice times you should get this, but this is something that we're going to do. Now, probably won't do many problems per se where I ask you to find the projected force, but this idea is what we're going to use to figure out how do we get a projected moment. Now, to preface that, if you think about what did I do here, I said if I have a force and I wanted the scalar value, I knew that then I just took whatever that force vector was and I dot product it with at whatever line I was interested in. So in that case, it was OA. So imagine now if we did this with a moment. So if we wanted to know the projection of a moment onto a line, then we can kind of use the same setup. So let's look at that. Now, so think about a moment of force about a line. Just like we found the projected force on a line, we could project a moment on a line. And so this image over here actually shows the idea very well. If we have this force in space going at point A, we know that in order to find the moment about point O, we would have just found the vector r from A relative to O, or going from O to A, and we would have crossed it with F. That would have given us this moment O over here. Now let's imagine that we had a imaginary or some line in space, and we want to know how much of that moment was projected onto that line OL. How would we do that? Well, you saw how before we took the whatever the moment was, and we dot product it with the line unit vector. So before we used the force, now we use the moment, and it works just the same because this moment here, MO, is a vector, but if we project it onto a line, it's going to be a scalar value. Okay, so this may take a little bit of thinking to see how it works, but if we follow the pattern that I showed you with the force, it works exactly the same, and the math works out really easily. So if you're having a hard time with the concept, seeing it, just do it with the math and trust the results until it kind of gels in your head. So the calculation we do is we take if we want the moment about line OL, we just take whatever lambda OL is dotted with MO. So looks very similar to what we did before, and you can reverse these. It doesn't matter which one's first. So this is the same as, remember, if we had a force, we had the force vector times the unit vector, and this is no different. And of course, we first start off with our moment. So if we expand this, then we end up with this idea where the moment OL is equal to the line unit vector dotted with R cross F. And that is shown in your book as this idea of the mixed triple product. Okay, so this isn't the same as cross product of three vectors. This is the mixed triple product. And so this is actually a fairly straightforward process. We know that, for one, is you can just do the R cross F, and then you just dot product with that, or you can just set it up all as one simple equation. So before we go on to that, let me show you what that means. So here's our mixed triple product. So if let's say we were trying to find that, we'd have S dotted with P cross Q. So here's our XYZ components, XYZ, XYZ. So if you were setting this up, then for a calculation, you would just say SX, and again, this is an I component, right? And then you would dot that with the I component here, which was PYQZ minus PZQY. And that's the I component. So whatever that number is times whatever that number is, you have I dot I, which is 1. And then you go on and do the same thing. And you have SY, and in that case, you'd have PZQX minus px, q, z. And again, that's your j, and that's your j. So those cancel. And then lastly, you'd have sz, and that would be your SC would be then multiplied by your PX QZ, I'm sorry, QY minus PY QX. And that's it. Then you just add, and that's K, and that's K, so that's K dot K is 1. So you essentially add that number to that number to that number. So you got to remember that when you find the moment about a line, it's always a scalar value, okay? So hopefully that the connection between this and the projection of the force is not too much of a stretch. Again, if trying to visualize it might be difficult, but if the more you think about it, if you don't go insane, it'll probably come together in your head. But as I've told a lot of students in the past, just accept the math, work it out, and have faith that the concept will come, because it's hard to really explain it. The more I explain it, the more it becomes a little circular, and you just have to kind of figure it out for yourself in terms of understanding. So let's do an example. So here we have the moment about a line, and what we want to find is what is the actual value of this. And so we have our force is given as negative 20, 10, 15 newtons in IJK components. And we have this pipe segment AB, and we want to know what is the projected moment on that line AB. So if you didn't know anything about statics and you just knew the math I showed you, then you would just approach it like before. You would say, okay, well, I know I have a force, I'm projecting it onto that line, right? So now I'm not projecting the force, I'm projecting the moment. So I know that my moment about AB is equal to lambda AB dot R cross F. And that's my general equation, right? And so this is no different. This is a vector. That vector dotted with that vector gets me the scalar, just like before. So what is our R? Well, if this is B here, and this is C up here, then again, recall how we do this. What we want to find when we're laying out this problem, the first step is, well, you can go in any order, but let's just walk it through. So you need to know the unit vector AB. And so this is A back here. So whenever you see AB, you know it's going from A to B. Now, if we went from B to A, we'd get the exact same answer, except it would be opposite in sign. And that has to do with your perspective. So if you hold a pencil towards your face like this, and you rotate it, then if the way I'm rotating it, it looks like it's going counterclockwise. But if I were on the other side of the paper looking at it, it would look like it's going clockwise. And that's the same thing here. It's a matter of perspective. So just go with the direction of the line it gives you, AB. So lambda AB just equals, and it's 3I plus 4J over 5. Not too tough. And so that's our unit vector. So 3/5 and 4/5. Then the next thing we want to know is, what is our R vector? Now, the thing about the R vector is it can go from any point on the line to any point on the force. So you don't have to worry about where you take it from. As long as you're going from a point on the line to a point on the force when you're finding your R vector, you're going to be okay. Now, you could find some random point way out here, but that why work so hard geometrically? What I recommend is take the easiest point you can. Now we know that the force is in contact at point C, and we know that point B is on this line. So why not just make this C relative to B, right? Now we write C relative to B means we're going to go from B up to C. So if that's the case, then R C relative to B just equals 4K, right? 4 in the K direction, and that's all. And so we're given our force. That was -20, 10, and 15. Sorry, make sure it's not negative. So now we have everything we need to put this together. So we go ahead and we set it up like I showed you in the previous slide. We know that the moment about AB, we have, and this is always the order you want to write them, lambda AB, R, C relative to B, and force, all vectors. We have our I, J, K. And so I is what? 3/5 for the unit vector, right? 3/5 and 4/5 in the J, 0 in the K. And then R is 0, 0, 4. And then F is -20, 10, 15. And don't worry about sig figs in here at all. Sig figs only at the end. All right, so if I go ahead and do that, I look at it, I go, well, I have 3/5 times that, so I'm going to say 3/5. That's going to be times what? 0 times 15 minus 4 times 10. So 0 minus 40, right? 0 minus 4 times 10 or 40. And then the next one, 4/5. So I have 4/5, and so let's see, is the 4/5. So the 4/5 is, so this is going to be plus, and then I'm going to say 4/5, but it's going to be 4 times minus 20, so a -80. All right, so 4 times -20 minus 0, so that. So I end up with -24 minus 64, which gives me -88.0 Newton meters. All right, so the moment projected, the scalar value of moment AB is equal to, you can either write it as -88.0 Newton meters or 88.0 Newton meters clockwise. And that's that. So comment on this is that no matter how complicated this thing is, it's still done the exact same way. Now, if you have, let's say, imagine you had multiple forces. Let's say you had, instead of just this one force F, maybe you had another force here. Well, you would just then add another, you just add another set. So if I had, like, say, F prime coming off here, then I would have just said MAB equals this plus, and then I would have had lambda AB R. So let's just say that if we had this going like that, we call that F prime, then we would, and let's say we'll call this point D here, then we would have just said, okay, let's add to that lambda AB dot R D relative to B, and then cross with F prime, and so forth. And so we would just added whatever that magnitude is on to the final answer, and we would have had it. So if you can understand this basic concept, then the more complicated problems are pretty much just a repeat of this, just with a few more numbers. All right. So that's that example. So yeah, let me make sure. Yeah, okay. So now this is this is the example. Now this should be on your worksheet. I think the previous one. So on this worksheet, you have just this one problem as I posted. And so this is a good one for you to just, again, try on your own. Now let's walk through it before you jump into it. You have this line AB, okay? And so this one's a little more complicated from the geometry standpoint, but not from the statics or a math standpoint. So you have the line AB, so pay careful attention to where these are located in space. And so we're told that this rod CD is 23 inches. So it's 23 inches from here to here. And then it's welded to the midpoint of a 50-inch rod AB. So this is going to be a similar triangle. So if it's 30 inches on this end and 0 on that end, then in the middle, this height here should be what? If it's halfway in between. So you're going to need that plus that to get the total height here. So then you're going to go ahead and you're going to figure out what is the rotation of AB due to this force P. Ignore force Q. That would be a separate problem. I could have told you Q equaled 600 pounds or whatever. So ignore it. It doesn't have any effect on the problem. So just focus on P. So how are we going to do this problem? Well, I would suggest 1, find lambda AB. What is it? Next, find an R vector going from any point on the line to any point on the force. And then lastly, find what is the vector form of P. And then go ahead and put it together. So take some time, work this problem out. If you can do this one, then you should be in pretty good shape on doing moments about a line. And then once you're done, come back and check and see what the answer is. Okay. So you paused, gave it your best shot. You know the answer. It was so easy and trivial that you're insulted. Hopefully that's the case. Maybe not. So here's the problem as drawn. And so again, here's your given. We want to determine the moment of AB by that force 235. So as we know, if we want the moment AB, that's going to equal the unit vector lambda AB dotted with R cross P. Now, I haven't put a subscript on R, so depending on where you want it to go from, that's certainly an option. And so you can do that wherever you really want. You can pick any point that's on there that is convenient. I chose G right here as mine. I found that this particular location worked well. So I'm going to say R is G relative to P. And so I know that in this case, my vector is going to go, actually, wait. No, that's not what I chose. Let me back up a second. What I meant to say is G relative to B. I couldn't read my own writing. So I know that B is on the line, and I know that G is on the force. So I'm going to go from B to G. Now, you could go from C to D. You could go from A to D. You could go from B to D. You can go from B to C. I'm sorry, not B to C. Go B to D, because you got to be on the force. So any of those. So I picked G relative to B. So first off, I'm going to figure out what is my unit vector for AB. So lambda AB equals AB over AB, right? And so that's going to be 32I. So going from A to B, I know it's 32 in the X direction. So here's my X. And then minus 30 in my Y. So my Y is up here. So minus 30 J. And then lastly, minus 24K. So the 24, where does that come from? The 24 is right here. So I'm going from A back to 0. Okay, so label my axes. So that, and then the magnitude of that actually turns out to be 50. So I end up with lambda AB actually equals, what kind of phrase is that? 0.64I minus 0.60J minus 0.48K. And you could leave it as a fraction or not, but this is a pretty easy fraction, 32 over 50. So 0.64, 0.6, 0.48. So there's my lambda AB. And then again, I said I'm gonna, for my R vector, I'm going G relative to B. In this case, it's going to be 5I plus 30K. And so B going to G. So I have to go forward in the X from 32 to 37, right? So that's the 5. And then the 30 is this way, 12 and 18. So I have that. So last thing I need is the force P. So P equals scalar P times that line. And in this case, it's going to be lambda dg, isn't it? D to G. So I'm just going to write it out. I know you can find lambda dg. So this is going to be equal. And in subsequent problems, I'm going to start just writing the unit vector. I'm not going to actually go through how I got it, because you should, by this point, know how to get a unit vector and a direction vector. That's what chapter 2 was. So I'm going to write this out as 235, because that's our force. And then that's going to be multiplied by 21 over 47I minus 38 over 47J plus 18 over 47K. And as I said, pretty soon I'll just go from P and I'll just say we have this 235, we multiply it by that. I won't even give you this intermediate step. I'll just tell you, I know it's 105I minus 190J plus 90K. So that's that in pounds. So now it's just a matter of setting it up. So I'll put a line here. Now we know that the moment then about AB, in this case, we have lambda AB, R, G relative to B, and our P, right? So we have 0.64, negative 0.6, negative 0.48, 5, 0, 30, 105, minus 190, and 90. There we go. So once we set it up, you know how to do this now. 0.64 times that minus that, negative 6 times that minus that, depending on which mode you use. You use plus, minus plus, or plus, plus, plus when you do your cross products, as I talked about earlier. So you have this set up, and so I'm not going to do the cross product for you, but this ends up being, since we were in units of inches and pounds, this ends up being 2484 inch pounds, or in proper sig figs, it would be essentially 2.48 kip inch, or you could convert it to feet by dividing by 12, and you get 207 foot-pounds, and it's positive. All right, so check your answer, make sure you got that. Again, notice that it looked a little more complicated at first, but once you found the three components you needed, you found the unit vector AB, you found the distance from the line to any point on the force, and the actual vector for the force. And that was it. Otherwise, it's just kind of rote repeat math. Now, I don't like rote repeat math because I want you to see the big picture, but for now, until you're able to conceptualize in your head the rotation of a line, just trust the math. Okay. All right, so summary to this point, we have a moment about a point. So if you're going to do that, you just need to identify the force vector by components. I've been harping on this a lot, but you should have this down. This should be something that you can do in your sleep. You get a force that's just a scalar, and you know its direction. You should be able to convert that to a vector. You should always be able to identify the distance vector. And again, this is moments. Remember that R is always the point of the moment to the force, always. So you always go from the point where you're taking the moment to the force. Then you just do R cross F, and your result is a vector. Now, when you do moment about a line, if the line, for example, is AB, you first find the unit vector AB, and that's for that line, you want to go from A to B. Then you want to find your force, whatever it is, as a vector, ijk. Then you find your distance vector, where R goes from any point on the line AB to any point on the force. This is an important concept. And then you go ahead and you do your lambda dot R cross F, and your answer is always a scalar. And that's it. So those are the two things we've done. So that's it for this part of chapter 3, lecture 6. In lecture 7, we're going to talk about the idea of equivalent systems or force couple systems. And so we'll work through that. We have a couple more lectures on chapter 3 before we get to the true equalers in chapter 4. So thanks for listening, and I'll see you in cyberspace. Bye.